Hello, everyone, and thank you very much for attending our control seminar series today. I would like to remind all of the MAE 205 students to log in using your full name. That way we will be tracking attendance. Thank you very much, Professor Kristic. Your turn.
Thank you very much, Lucia. So it's a great pleasure to welcome today Dr. Nicholas Carlson, who is the Vice President for R&D and the Chief Scientist at the Yahoo demand side platform. The trajectory of Dr. Carlson starts at Lund University in Sweden, in a field very, very different than the one where he's making his current incredible contributions and impact. He starts out in Lund with an undergraduate degree in engineering physics and completes his PhD at UC Santa Barbara and is one more proud member of the mighty UCSB engineering club that has several members on our faculty as postdocs or PhDs or undergrads, Jorge Cortes, Sonia Martinez, Nick Gravish, and myself. Dr. Carlson is a recipient of the Distinguished Alumnus Award from the Department of Mechanical Engineering at UCSB. His early post-PhD career was in robotics at a company, Evolution Robotics. But after that, his career has taken him to the online advertising through a company that was acquired by Yahoo. And in the course of his career, he has produced 44 issued patents. Quite an impressive record. So, Nicholas, I welcome you warmly to our seminar series, and we'd love to hear and learn from you what your algorithms do, as they probably serve us lots of advertisements, and essentially we are probably the plant or one little part of the state, huge state vector in that plant that you're controlling.
All right, thank you so much for the kind introduction. So let me start by sharing my screen here. And if you can just confirm that you're able to see my slides.
Yes, we can.
All right. So, well, thank you again very much, Professor Kristic, for the kind introduction. And I'm obviously very happy to be here to tell you about how feedback control is used in online advertising. The title of my talk is Control Problems and Adaptive Control in Online Advertising. So this is an outline of the talk. First, I will explain the basics of online advertising and which aspects of automated online advertising I will cover in this talk. Then I will define the problem that I will solve, and it's one of the most common problems in practice. I will show with a minimum amount of math how this problem can be decomposed into a two-player non-cooperative game where one of the players is a feedback controller. Based on first principle reasoning, I will discuss properties of the plant to control as well as challenges and opportunities. I will propose a control system, and I will share some conditions of stability of the closed-loop system. I will then show some simulated results and will explain how the problem and solution discussed in the talk can be generalized to a much larger family of important optimization problems. Finally, I will provide some references to relevant literature that will expand on what I've been covering in this talk and some concluding remarks. All right, so here are two basic examples of online advertising. So note, ads are used as a means for publishers, so this publisher in particular, to monetize on traffic to the site. So basically, the publisher is selling real estate on their webpage to advertisers that are willing to pay for the opportunity to have their ads shown to an internet user. And in general, the way that the ads are selected to be shown on this page does follow the allocation process illustrated in this slide. So everything I describe on this slide happens in just a few milliseconds. So suppose that you are sitting in front of your computer on the left, loading your favorite web page. First, a call is made to the publisher content server, which returns the requested article or video or photo, whatever you have requested. Simultaneously, a call is made to the publisher ad server, which assembles information about you and this particular ad request. And exactly what information is assembled depends on the privacy setting that you have in your browser. This ad server forwards the request for one or more ads to a so-called supply-side platform, or SSP, which is a system tasked to find the highest paying ad for this ad request. The SSP arranges an auction and accepts bids from different advertisers. And those advertisers are often represented by so-called demand-side platforms, or DSPs. The role of a DSP is to decide how much to bid on behalf of an advertiser to maximize the return of investment of the advertiser. The highest bidding advertiser is awarded the opportunity to show their ad to you and is charged an amount equal to, in this presentation, the second highest bid. There is an industry trend towards first price cost model as well, but in this presentation, I will assume that it's based on the second price. So in this talk, I will focus on what the DSP is doing. So think about everything from here on to be the problem that the DSP is solving. And there is no collaboration across different DSPs. So I don't know any information beforehand about what other advertisers or DSPs may be bidding for individual impressions. Okay, so next. So here is a problem statement that I would consider in this talk. So it's a popular and illustrative example of what an advertiser cares about. And kind of the key message here is to take a holistic approach and to first understand what is the precise and ultimate problem to solve. So the goal in this case is to maximize the total number of conversions or sales produced as a result of shown ads. And the constraints are defined by a monetary budget and an upper bound on the average cost per conversion, also denoted ECPA, or effective cost per conversion. For example, an advertiser may come to the DSP with a daily budget of, say, $10,000. And the objective of the DSP is to figure out how much to bid on different impression opportunities in such a way that the total number of conversions is maximized, while the cumulative cost for all the awarded impressions does not exceed $10,000. And so that the total realized cost divided by the total number of produced conversions does not exceed the so-called ECPA constraint. And I mean, this is essentially a standard constraint optimization problem. However, each bid is a decision variable, and there may be billions of impression opportunities every day. So it's an extremely high dimensional problem. Moreover, the probability for an impression to turn into a conversion is a priori unknown and must be estimated. So in short, it's virtually impossible to solve this problem using a centralized optimization algorithm. But fortunately, there is a way to decompose the problem in sub-problems that can be solved more easily. So we can understand what this decomposition is by considering this figure. So recognize first that every impression opportunity we may want to bid on has a cost, BI star, shown on the horizontal axis, and that's the highest amount someone else is willing to pay for this impression. And there's also conversion rate or event rate, PI, shown on the vertical axis, which is the probability that the impression turns into conversion or a sale. And assume now that all of the potential future impression opportunities are shown as black dots in this figure. Impressions with a high event rate and a low highest competing bid price are located up in the upper left corner of the plot. And since impressions in this corner of the plot have a high chance to turn into conversion while being available to be purchased at a low cost, they are the most appealing impressions to buy. On the other hand, an impression in the lower right corner, they have a low chance of turning into conversions and are expensive to buy. In other words, they are the least appealing impressions to buy. So to understand from this illustration, what is the optimum bidding strategy? Note that two impressions along a straight line going through the origin, they have identical average cost per conversion, okay? And to bring this kind of further, what this really means is that if we are bidding proportionally to the conversion rate, PI, we are the highest bidder for all of the impressions in the green shaded region, and they are the most valuable impressions. So all we need to do is, by adjusting the angle of this straight line that I labeled with a U, to the largest value for which the constraints are not violated, we have de facto found the optimal solution. So with this in mind, hopefully the decomposition is obvious, that one system is in charge of estimating the event rate, PI, conversion rate, and another system to compute the angle of the line, U. And we don't need to estimate the highest competing bid price, because that will work itself out. So we can now take this insight and turn it into a block diagram. And the modularized solution then can be described as shown. So the event rate estimation component leverages big data, historical user level data, so granular level and machine learning, to compute the best possible event rate estimate of each individual impression. So that's it typically is doing that by training machine learning algorithms offline, and then using those models online to score individual impressions in real time to compute an estimate of PI. The control component compares constraints with cumulative campaign level data to adjust the control signal U, or the angle of that line on the previous slide, to largest value for which the constraints are not violated. So in the remainder of this talk, I will focus on the control system, and I will assume that the event rate estimation system is already available and in place. But to appreciate some of the challenges with a control problem, let's consider what happens for different values of the control value U1 and U2 as it relates to the total cost, total spend, the average return of investment, or the ECPA for different values of U. So here's the thing, that I mean, if you compare kind of two values, then depending on how many impressions are available in that little slice between the first and the second line, that sort of will dictate kind of whether there is a sort of staircase between those lines. So obviously that this kind of the behavior that the response curve. So if you look at the top one, cost versus control signal, it's a discontinuous function, and it can make control quite challenging. I mean, the good news is that both of the functions here are monotonic functions, assuming that the event rate estimates are accurate. In practice, actually, the event rate PI that is used for the bidding are only estimates, and that could compromise the monotonicity of the second curve, the ROI versus control signal. So this is the name of the game, that at the end of the day, that we want to use the control signal to adjust to find kind of the value for which we are spending a desired amount of budget, and that sort of will then, depending on the shape of this response curve, that problem is more or less difficult. But let's now sort of more clearly articulate the control problem. And to simplify the discussion, let's from here on assume we have only a spend constraint. Okay, the control problem is to update U every, say, 5 minutes based on campaign level spend data, and the set point is given by daily budget divided by the total number of time intervals in the day. So that what the advertiser cares about is to produce the most number possible of conversions per day for a given daily budget. And while the control system then has the time axis can adjust U to sort of find that. And it's the optimal solution is to find that one U that achieves this. Okay, and before we can design a control problem, we have to recognize what are the challenges. And as always, when we are designing a control system, we have to be mindful of the risk for instability. There's also a temporal component in that all the impressions, they're not available all at once, and they're not available uniformly over time, but they are subject to a significant time of day pattern. I mean, there are fewer people online in the middle of the night than in the afternoon. And there's also a high amount of noise. And the noise is multiplicative and non-Gaussian. There is also latency involved. I mean, both on the actuator side and on the measurement side, although the latency is not, I mean, dramatic if we are only considering the span constraint, because this latency is typically just associated with the time from when we're submitting the bid until we know kind of how much, if we won the auction, and how much we have to pay for it. So we're talking about maybe 15 to 30 minutes or so, because we don't get it in, we need to aggregate it across a lot of different ad servers. So it doesn't, from the perspective of the control system, we don't know kind of very well immediately. But kind of this is a control problem, and in order to design a controller for this, and to do it sort of using analysis, we need some form of plant model. So a qualitative model is a starting point, and I mean, as the plant as perceived by the controller is the dynamic relationship between U and the output Y, which is the spend in dollars in the previous 5 minutes. And without loss of generality, we can describe this as a time-varying nonlinear difference equation. So this kind of in the kind of complete fold generality. But let us here now consider sort of some properties. So here are a couple of examples of real steady state input-output relationships of the plant. You can see that they have quite different sort of look. The slope of the curve is what we refer to as the plant gain. So that the steeper the curve is, I mean, the more careful we have when we need to be when we're updating the control signal U. But now for some campaigns, it may have big steps, and for challenging response curves, that they may indeed not even exist a fixed point solution at all. So for all this, for a desired value of Y, there may not be any U that will provide that value. I mean, for any one value of U, either we will spend too little or too much. And if all campaigns are well behaved, I mean, we can still proceed and under the assumption that the response curve is smooth, but that is in general not possible. In which case we may adopt the following techniques that I will show. So since we are bidding, I mean, this is enabled by the fact that we're bidding on millions or billions of impressions every day. And since we're doing that, we may randomly perturb individual bids a small amount to produce what is effectively a smooth response curve. And a convenient way to do that is to generate, for example, a gamma random number with expected value equal to the unperturbed bid, but with a relative standard deviation of a few percent, so given by some configuration parameter. And by doing that, what we obtain is the response surface. So you see it here on the left is that challenging response curve on the previous slide, but on the right, we have added one dimension to it, which is here labeled UU, which is really just the relative standard deviation of the randomization. Okay, so that means that for as long as that parameter is non-zero, we have effectively produced a smooth response curve. And by doing this, I mean, we can proceed sort of as if the response curve between U and Y is locally linear. So kind of this allows us now to establish sort of a practical and useful plant model sort of structure to capture the dominant properties of the plant. So far, I will now sort of start to kind of ramp up to use more math, but really the dominant properties of the plant can be pretty well described by first order in the state. It's so linear in the state and the control signal time periodic difference equation. And let me use a pen here to try to better point out what we have here. So first thing in this model is that we have linearized. So this is a model kind of locally around each operating point. So we have kind of this linearization, which depends on the operating point on the previous slide on the surface. But to account for significant time of day pattern, then what we have to do is to also incorporate a periodicity. And this function H captures this. So it's a 24-hour periodic function described by H. But internet traffic is noisy and tend to be multiplicative in nature. So that's why we're having this multiplicative component on the right. And the dynamic of the plant is related to delay between when a control signal is updated and when its impact on awarding impressions and span is observed in the feedback signal. And again, for the case considering this presentation is primarily associated with delays in our own platform, which is the actual and measurement delay. In a more general setting, there is also a latency associated with the user behavior. Kind of when you show an ad, it may take hours or days before they decide to buy something. But the first order approximation, the latency that is, I mean, a good approximation for the problem considered here can be described by just a first order filter, which is then captured by parameter A3. So that's the time constant, and it's typically in order of, say, 15 to 30 minutes for this problem. And worth noting here is that in practice, we can typically estimate the dynamic A3 and the seasonality H reasonably well offline and beforehand, while the linearization defined by A0 and A1 must be estimated online. So more on that later. So given this plant model, let us now propose a controller that may work for this one. And it contains sort of three parts of it. And I'm starting here in the middle. And the first one is a periodic feed-forward compensation. So what that is doing is distributing a daily budget intelligently across the day, according to the plant periodicity and latency. So this UC bar, which is the set point signal that I talked about before. So that's a daily budget divided by number of time intervals in the day. But remember that the advertiser cares about producing the most number of conversions possible in a day for a given daily budget. And the advertiser leaves it at the discretion of us, the DSP, to distribute how much to deliver it each time during the day. So here's kind of the hypothesis here is that by using this feed-forward compensation that we can achieve optimality to be so verified. But what it's doing is that it's just taking that sort of initial set point signal, which is then typically fixed throughout the day, multiplying the seasonality and adding the latencies, the dynamics to it. And so then we're having kind of a modified set point signal UC, okay? And then we're using that in an error feedback controller. And this is an integral servo controller. It's a pure integral error feedback controller. So just comparing this modified set point with observed spend in the previous 5 minutes. And finally, adding a perturbation. I will refer to that as persistent excitation. So it's really just taking the U0, which is a sort of baseline control signal, adding a slight noise to that one, which perturbs then each control signal using a stationary first order filter that is driven by white noise. Now I can elaborate on this later if you wish. So now, all in all, what we have now, we have this the plant, and we have the controller, and we can describe all of that as a block diagram. So here we have the interconnected system, and the control problem is to achieve a small error E here, but also a constant control signal U. And then, I mean, if you now remember one of the first figures that I shared, kind of that the optimality, which I just kind of did prove by figure, but it can be shown here that if we find the one sort of constant value of U that is used throughout the day, that must be optimal if the error is 0 as well. So this is kind of what we have. But I haven't so far demonstrated whether kind of the control objective is achievable using this, and whether it leads to stability, or what the stability conditions may be. So we need to prove that, and I want to go through sort of some of that just to demonstrate that. I mean, it's a lot of interesting mathematical problems associated to controlling online advertising. So what I will do first is that I will first write down the closed loop dynamics in state space 4. And what I'm doing is I'm just combining the dynamics of the plant and of the controller, and writing it down like this. And I will not go through the details on this slide, but what you see is simply just the combination of states state X1 is the plant, and the X2, X3, X4 is the controller. Okay, and in this case, I mean, what the dynamics here now is nonlinear, it's periodic, it's subject to non-additive noise. Clearly, it's not a linear time invariant system, which we otherwise like to work with. So it makes it hard to analyze. So, but the question, I mean, how do we proceed? I mean, where do we take it from here? And kind of there are sort of some insights that we can make right away just by looking at this this dynamic equation. And the first thing to recognize is that states X3 and X4, they're independent of other states. So that means that if with that sort of insight, I mean, they actually have closed form solutions. So that's the first observation. And then what we can do with that is that, well, then let's treat those X3 and X4 as just exogenous input signals to states X1 and X2. Okay, and then let's introduce a variable transformation. So let's introduce X1 tilde and X2 tilde as shown, as just kind of this mapping, unique one-to-one mapping from the other states. Now what we can do, we can rewrite that messy differential equation a couple of slides ago, and we get something that is a tiny bit more well-behaved. So now what we have is that the dynamic for X tilde here, it looks like this. And so it's a stochastic, periodic, but it's a linear in the state difference equation. And it is still not possible to produce a closed form solution of X tilde, but stability conditions of the expected value and the conversion can be established. And I will provide a reference at the end of the talk on the details, both about on the results and also on the proofs on this. But the kind of the key result here, or one of the results on kind of the condition for stability of this one is it can be simply stated as this: that that if kind of the set point UC bar is constant, then the expected trajectory has a unique limit cycle, and the expected control signal and expected error has a unique fixed point solution. It's given by what is shown here. And this solution is globally asymptotically stable if and only if the eigenvalues of the product of all of those matrices have eigenvalues that are strictly inside the unit circle. Again, that I refer to the reference for the proof, but it's a pretty straightforward. Basically, the ideas of it is that we can start by just establish the stability of the limit cycle of x3 and x4, which is easy because we have the closed form solution, and it's a linear sort of relation, basically a linear filter of white noise in this case. The next thing we can do is that we can establish global asymptotic stability of the expected value of x tilde by just adopting and making use of the law of total expectations. What that leads us to is a linear deterministic periodic difference equation for the expected value of x tilde. Then we use just Floquet theory to establish that the stability of this one is dictated by the eigenvalues of the product of all of those matrices throughout kind of the time from 1 to t, where this matrix A is t periodic. So using that, we can make also the variable transformation back from x tilde to x, and then it's trivial to show that the expected values of x1 and x2 converges to the limit cycles previously presented for x1 and x2, and that the expected control signal and feedback error converges to the fixed point solution. Okay, so then a lot of Greek, a lot of equations. I don't expect that you will digest all of this kind of in just those few minutes, but really what it comes down to, sort of some insights. That one insight here is the dynamics dictating stability of the expected trajectory and of the covariance as well, by the way, which I didn't cover, is given by this periodic linear difference equation, and this equation is defined by 3 key quantities. It's the latency parameter A3, like this. It's a product between the plant gain and the integral gain that you have here. I'll refer to this as the loop gain, and the plant seasonality H. Kind of those 3. I mean, it's a relationship between these 3 that will dictate stability. And global asymptotic stability is achieved if and only if the eigenvalues of this product here are strictly inside a unit circle. And there is no closed form solution available to compute eigenvalues, but they can be easily computed numerically for different values of A3, the loop gain, and the seasonality. Then, given that it's sort of trivial to show the convergence of the control signal to a constant value. And so, although we cannot compute a closed form expression to this for the eigenvalues of this product of matrices, what we can do is that we can build some intuition by testing it out on some examples. So to understand the stability results, let's consider an example. So assume that the seasonality H is just a simple sinusoidal. And let's assess the stability of the closed loop system for different combinations of the amplitude of the sinusoidal. So the amplitude is here H1, and you have each subplot here is for different amplitude of the sinusoidal. And I want to see how the stability depends on the latency parameter A3, which is on the horizontal axis, and the loop gain, which is the product between plant gain and integral gain. And then what we can do, we can compute just numerically the eigenvalues for various configurations and determine if they're inside or outside of the unit circle, and thereby decide for what configurations the system is stable and which ones are not. And in those plots, blue means unstable, yellow means stable. So the interesting thing here is that that those plots in general have sort of three regions. We have one fully blue region, kind of that's where we have instability for sure. One fully yellow region, which is where we have stability. But they also have a region where the blue and yellow are mixed together, and the mixed region contains non-robust stable configurations. We definitely never want to operate in the blue or the mixed region, but rather be in the yellow region, sufficiently far away from the blue area. And I mean, as a reminder here that A3, that latency and the seasonality, they can typically be estimated reasonably well offline and beforehand, not perfectly. So we have to be mindful about the uncertainty, but reasonably well. But the plant gain, A1 in this case, needs to be, I mean, which also kind of stability depends on heavily, needs to be estimated online. So, that's kind of where we are. So now we have kind of, okay, we know what stability depends on, and also what we may know or what we may not know beforehand. So now adding that kind of level of sort of additional insight into the block diagram, we can expand on the control system where we are recognizing that the integral gain, I mean, need to be selected dependent on what the plant gain is. So again, the plant gain is A1 needs to be estimated using some system identification component. And obviously then, I mean, if the plant gain is large, we use a small integral gain and vice versa. This can be achieved, for example, using some recursive least squares estimator to estimate the plant gain. And here is kind of where I will further justify the persistent excitation controller, which perturbs you a small bit to make kind of the estimation possible, also when U is almost constant. And you may wonder kind of, well, why don't we use, say, a deterministic perturbation? We could use kind of some maybe added sinusoidal or something else, or just whatever you may feel like is appropriate. But the thing is that we also want to avoid competing bidders to be able to anticipate what we will do and exploit that to their benefit. So that's why we're choosing a stochastic perturbation of the control signal. The next question you may have is, well, why don't we use white noise? Rather, why do we use this colored noise? Well, if we're using white noise, then the system identification component will depend heavily on a perfect understanding of the plant latency A3. And since we don't know perfectly well what this one is, we only know roughly what it is. We have to be prepared that when we are measuring values of Y, we don't know exactly to which value of U that corresponds to. So then by using colored noise, basically a low pass filter, we can reduce the dependency on a perfect understanding of the plant dynamics. So then that gives us, depending on how well we know A3, kind of that will help us to decide what value of A4 in the persistent excitation controller to use. So time doesn't permit me to sort of dig into kind of system ID component, but obviously there are many choices, but what I mentioned is that using some sort of standard recursive least squares algorithm is one possibility. And what I will do next, I mean, I will instead just go ahead and demonstrate the behavior of what we have put together here in the closed loop system in a simulated example. All right, so the goal of this example is to illustrate how to control a discontinuous and time periodic plant. In particular, I want to demonstrate the value of using the periodic feed-forward compensation, excitation control, and plant smoothing, or this bid randomization. And recall that optimality corresponds to value of the control signal U that is constant within the optimization windows, typically per day. So again, if I recalling one of the first plots that I showed kind of with all those dots, I mean, we don't want the angle of that line going through the origin to oscillate. Kind of optimality is when we find that one angle so that we're winning just the right amount of impressions. That's why I want to have U to be constant. And also, we will assume that the latency parameter A3 and the seasonality function H are a priori known, while we have to estimate the plant gain online. And we'll do that using recursively squares algorithm. And we'll compare 3 different controller configurations, with and without plant smoothing, and with and without excitation controller. So here are configurations. First one is pure integral control with no plant smoothing, no excitation control. Then pure integral control with plant smoothing, but no excitation control. And the third configuration is pure eye control with plant smoothing and with excitation control. Okay, so then the setup that we'll consider is shown here. And in the first plot on the left, the black staircase function is the unmodified plant, and that's it's a result of how much competing bidders are willing to pay. And I have overlaid the plot with 2 examples of smooth, effective plants as a result of bid randomization. You can see for different values of how much you are randomly perturbing each bid, then we're obtaining an expected sense the curves of those smooth functions. The right plot shows the effective plant gain as a function of U for different values of the plant smoothing parameter. I will assume that the plant is described by the dynamic shown here below. So again, we have multiplicative noise, we have a sinusoidal with an amplitude of some 80% so up and down throughout the day. We're having dynamic with about a time constant about half an hour. And the system is implemented as a discrete time system with 5 minutes sampling time. And we'll assume that we're having a set point that is 450 for the first 100 hours, and then goes down from 450 to 100 after hour 100. Okay, so now let's compare first when we're running controller configuration 1 and 2 side by side on this problem, and let's compare kind of what do we get. So remember, configuration 1 is only pure integral control, and configuration 2 is when we're doing bid randomization to smoothen the plant. So what we have here, we have 3 subplots. The first one is a control signal, then the observed spend every 5 minutes, and the estimated plant gain. The red curves correspond to the control with no plant smoothing and no excitation control. And this is the most challenging scenario. So keep in mind here that for this case, the plant gain is not even always defined at all, because the plant gain is either 0 or infinity. Okay, and so as a result, the plant gain estimate gets totally out of charge. You can see in the third subplot that the red curve just disappears. And with a feedback controller thinking that the plant gain is astronomically large, it will make then very small adjustments to the control signal. So effectively, it makes doesn't respond at all when the set point signal changes. So control signal remains the same. I mean, it will not deliver the right amount. The black curve is the second configuration. So in this case, we're using plant smoothing, but no excitation control. The plant gain in this case is always defined. However, without excitation control, the system is not persistently exciting. So the system identification is extremely poorly conditioned. So the plant gain estimate, although better than in the first scenario, it's still way different from the optimal plant gain. So the optimal unknown plant gain is shown in the green curve. So plant gain here for the configuration 2 is the black one. It's wrong, but eventually a controller catches up. So we can see that the black curve goes down to meet the needs of the new set point. And but it takes about 50 hours before it does catch up. And we can also see in the second subplot, which is the spend for each 5-minute interval. And for the configuration 1 on the controller, when there's no plant smoothing, you can kind of see that how much the spend oscillates, because the controller kind of making small microscopic sort of adjustments above and below kind of the threshold in the response curve. So either it's under deliver, over delivers. But so, I mean, all in all, none of these two configurations of the control is really doing a good job. Okay. So then what we'll do next is that we'll compare configuration 2 of the controller with the configuration 3, where we're also adding excitation control. So that's what we have here. So the red curves in this plot are the same as configuration 2 in the previous. So basically the best configuration on the previous slide is here shown in red. So, and it's compared with configuration 3, which is the black one, and which also involves excitation control. And you can see the excitation in the form of small wiggles of the control signal U in the first subplot. And thanks to this sacrificing control signal volatility, the plant gain estimation is now better conditioned and achievable. So you can see that kind of as a black curve in the third subplot. So thanks to better plant gain estimate, the feedback controller is able to respond faster. You can see here in the first subplot to the set point change at hour 100, and then catch up and do the desired delivery. So in summary, the controller configuration with plant smoothing and excitation control is superior in this example. Okay, and I mean, much more can be said about both this specific problem that I've solved and simulated, and practical and theoretical complexity related to this. But in the interest of time, I mean, I will sort of start to wrap things up and also give you a chance to ask questions. But before I do that, I mean, let me point out also that the problem that I've considered here is really just a special case of a large family of important and interesting problems. So let me just dedicate one slide to that sort of generalization. So here what we have this kind of a much more larger set of problems. So what we see here is that we may want to have some more general objective function, want to maximize something that is some expected value minus some expected cost. So this could encode some combinations of performance and branding and whatever the advertiser cares about. So it's a very general function. Then it could be subject to I mean, any number of constraints. The first constraint here is the familiar spend constraint that we have discussed so far. The second set of constraints, which is then many constraints really, are what we refer to as ECPX constraint, or effective cost per event constraint. And so an advertiser may want to pay, for example, at most $5 per conversion, or at most $1 per 1,000 impressions. So those are kind of examples of the second set of constraints. The third set of constraints are so-called event rate constraints. And an advertiser may want to have at least, say, a certain percentage of all impressions to be served to sports enthusiasts or to people in California, etc. So then kind of we're having a large number of constraints, and we want to find out again, I mean, what is the optimum bidding strategy for this one. And the traded impressions now also may be solved based on some combination of first and second price. So some impressions, winning bidder pays the second highest bid. For other impressions, the winning bidder pays its own bid. Okay. But then, I mean, the good thing is that with this, I mean, we can use Lagrangian techniques to still decompose this problem into, in this case, a 3-player non-cooperative game, as shown in this block diagram. So this obviously resembles what we have seen earlier in this presentation. The only difference is that some of the signals in this block diagram are now vector valued. So, for example, the reference signal or the set point signal here is a vector of all of the constraints that we have. Okay, so it's going to be any number of constraints. The campaign feedback is a vector of delivered number of different events and span. So that's a vector as well. The impression valuation component that can take the place of the event rate estimation component earlier produces a vector of some estimates. So it could be the click-through rate, conversion rate, the likelihood for the user to be sports enthusiast, etc. And the campaign controller produces a control signal that's also vector value. But it can be shown that it can produce such a vector so that what needs to be done in real time is to just produce an affine map between those two signals to produce a scalar, what I call unshaded bid here. And then if the impression is all based on first price auction, then this bid needs to be shaded. Basically, we have to figure out, because if we think, if the computed bid here is say $1, and the impression is sold based on first price, and if we have reason to believe that the highest other competing bid is only 50 cents, I mean, it wouldn't be wise to submit a bid of $1 because we know that we will win the impression and we're going to be charged $1. Instead, we would reduce this bid to 51 cents because we would still win the impression and we will be charged only 51 cents. So that's why we're having this bid shading optimization component that is taking into account our best belief of the competitive landscape to reduce this bid to something else. And that's what we're submitting here. And I mean, this sort of decomposition, I mean, it's you can obtain by just using techniques from Lagrangian optimization, and what really is going on under the hood of the campaign controller is to figure out what are the optimal Lagrange multipliers, and then based on that you can map the Lagrange multipliers and the constraint vector into a control signal vector that can be easily just combined using this affine map with the impression value vector. Okay, so it's kind of, this opens up, I mean, to solve, I mean, a large range of problems in kind of in a holistic manner, rather than trying to kind of solve them, I mean, in parallel without kind of coordinating among the different constraints. I mean, well, I will provide references to this as well, and kind of now, this is kind of the only thing I want to say, kind of what goes beyond what I discussed earlier. So let's just now kind of just summarize kind of with, so if you happen to find anything I said kind of interesting, want to learn more, I mean, here are some references, and it's just in chronological order, and most of what I have covered is covered in my Control Systems magazine paper, so reference number 3. And if you're interested about kind of the generalization that I mentioned in the previous slide, then you may want to take a look at the CDC paper from last year. And I mean, there's obviously much more literature out there, but I think the interesting thing is that very few papers are written by people kind of from our community, with a control systems background. And I mean, a lot of results, I mean, related to controls, I mean, is empirical in nature. And you will also, I mean, if you start to do the literature search, you will find that, I mean, a lot of authors are effectively reinventing feedback control or demonstrating a poor grasp of systems theory and limited appreciation of stability. And I mean, what I really hope that you will, I mean, walk away with from here is kind of to see that this is a great opportunity for any one of you or your students to look at. I mean, there is a massive amounts of opportunities of research problems that I mean, that is in dire need of people with a controls background. Okay, with that sort of preach for engagement, I mean, let me just conclude to say that online advertising involves high-dimensional and challenging optimization problems. That's number one. The second thing is that ad campaign optimization may be decomposed into 2 or 3 player non-cooperative game. feedback control plays a critical role to solve the problem. Also that online advertising has many open and impactful research problems in control systems and dynamics. And with that, I thank you for your attention, and I'll be happy to take questions.
Thank you very much, Nicholas. Wonderful talk. Any questions from the audience?
You can either raise your hand or write in the chat that you would like to ask.
Or just speak up.
Yes, I think everyone are kind of processing this interesting talk.
Mm-hmm.
I have a quick question, if I can go first.
Please go ahead, Jorge.
Yeah, thank you for the great talk. It's very interesting. I was curious, at the beginning you said that you were going to consider mostly the second prize, no? And then at the end you mentioned the first prize, and I was wondering how does that affect the overall setup? Is it because of the shading stuff that you were discussing, or?
Yeah, so the interesting thing, which is not kind of demonstrated here, is that when you, I mean, if you take this problem here, which is gender, where, I mean, it could be a combination of first and second prize. Kind of when you do the math, I mean, what it ends up being is that that you're going to have exactly the same kind of decomposition. The only difference is that for impressions solved based on the first prize, you do bid shading. For impressions solved based on second prize, you use the bid kind of before. You don't do any bid shading. Kind of everything else remains the same. So,
I see. Mm-hmm.
So the impression evaluation problem, you can think about that as sort of user-centric, because and that sort of is helpful kind of when you are working kind of in a research group, that that it doesn't matter. This problem here, impression evaluation, doesn't need to care anything about the constraints. I mean, it's only has conditioned on an impression being awarded. What is the likelihood for something to happen? Mm-hmm. And the campaign control component does not need to know anything about the likelihood of an individual user to act. It's because it only relies on aggregate information. Mm-hmm. And the bid shading problem, under the assumption that campaign control and bid impression evaluation are doing their job well, mm-hmm. so that assuming that this BIU here is computed properly, then bid shading optimization only depends on the competitive landscape, mm-hmm. And that sort of helps us to sort of divide and conquer when mm-hmm. we are developing the algorithms. Mm-hmm.
Great.
Okay. Thank you, Jorge and Nicholas. I have a question, but I want to give an opportunity to others to ask first. Okay, I'll go next. Nicholas, you made a very convincing case through the simulations for basically every ingredient of your design to be very important. The smoothing part, super important. The excitation part is super important. And also there is the seasonality aspect, the feed forward part that was evidently important. And that part you illustrated with a sinusoidal signal, which was, probably for educational purposes chosen as something simple, but surely it's not a plain sinusoid that you use in the actual practice. And here's, so it's not only that there are variations in the course of a regular day, there are weekends, there are seasons of the year where the activity on the internet depends on the length of the day. There are holidays which are predictable changes in the seasonality. So how is this handled? I also noticed that in the list of references you had a paper identification of seasonality. So obviously you don't leave this HFT to chance. It's maybe the most important thing in the whole recipe.
Sure. I mean, a lot of things can be said about it, and then also, admittedly, I mean, everything I'm working on it's still sort of. I mean, there is a long way to go to have sort of perfect solutions. So, but so one thing is in terms of the time of day pattern. I mean, our experience kind of when we look at data, it's although as simple one term harmonic is not a good approximation, but we actually get a very good result by looking at two terms, kind of a truncated Fourier series, where we're looking at having just to 24 and 12-hour sort of term. And I mean, we have, and I mean, that's sort of, sure, we can get a better result by adding more terms, but sort of some advantage is by using some kind of truncated Fourier series, then we sort of automatically get kind of that on average throughout the day, it's 0, because I mean, you remember that the seasonality adjustment was 1 plus sort of h, kind of when if this h is just kind of the sum of sinusoidals kind of with a 24-hour periodicity. I mean, sort of that helps kind of in some regards, but we need to estimate kind of those, even if we have reason to believe that a 2 or 3 term kind of truncated Fourier series would do the job. I mean, it's here I made it easy for myself to say assume that it's known, but yeah, well, it's not perfectly known. So I mean, one thing is that we may do kind of, we may get a good sort of starting point offline, but it's something that we may want to improve kind of online as well, and different campaigns have different seasonality patterns, and although I think that I said that the seasonality only depends on the internet traffic, but that's actually not quite true either, because if all other competing bidders, I mean, were bidding kind of consistently the same throughout the day, yeah, then it would only depend on the traffic and the number of users. But in reality, kind of that the competing bidders change throughout the day. I mean, if there is a tendency that the competing bidders drop out of the sort of bidding near the end of the day, that means that there will suddenly be, I mean, more impressions available at a lower price point near the end of the day. That will impact that seasonality. So I mean, that to really do this well, I mean, then we have to estimate the seasonality, taking both kind of the time of day, internet traffic, and competition into account. And that also then means that sort of plant gain that sort of is meant to kind of represent kind of the distribution of competing bidders, that sort of goes hand in hand with the seasonality as well. So I mean, ultimately, seasonality and plant gain, I mean, they should be estimated, I mean, simultaneously, because they're sort of coupled, and it's non-trivial, but it's and yeah, and you mentioned, yeah, it's their week patterns as well, so that's something, and different ways how to handle it and depending on kind of the preferences of the advertiser. Some advertisers, I mean, that they insist they want to have the same delivery 7 days per week, and then I mean, what we just have to recognize that the relative, then kind of the time of day, relative time of day pattern on a Saturday and Sunday may not be any different than the relative time of day throughout a weekday. It's only that the kind of the level goes up and down.
Yeah.
And in other cases, kind of we're making adjustments. And the same thing applies to, I mean, special holidays that some advertisers want us to kind of compensate for that. Some say not, no.
Mm-hmm. I want to ask you one more probably curveball question. So you started with a model, which was a discrete time, nonlinear time varying model. Are you able to liken these dynamics to anything familiar from mechanical systems, electrical systems, thermal, fluid, biological populations, circadian rhythms in human or other animal organisms or plants and so on. Maybe you haven't given it a thought. That's why I mean that it's a curveball. But you know, perhaps you did.
Yeah, no, well, I mean, I've been thinking, I mean, I haven't, I'm sure there must be, and actually, you probably have, I mean, based on your experience, you may be able to help to sort of find kind of that, what are kind of, I mean, the other examples that sort of would capture this, I mean, have similar behavior, but let me kind of also point out here that I would say that the most important properties of the plant is not the dynamics. So if in the closed loop system, if you can look at here, that is much more dynamic in the controller. I mean, it's the indirect controller is much slower than the plant dynamic. So it's, I mean, you may even kind of first order approximation may say, well, okay, suppose it's only one step delay in the plant. I mean, so there is the main challenge is not the dynamic. The main challenge is the seasonality and the high noise level for this particular problem. But then when we are going from this sort of simple problem of only adjusting the spend, which I looked at here when I'm saying that, yeah, that the time constant of the plant is, I mean, 15, 30 minutes, I can so design a control, because I said that if the dynamics of the plant has a time constant of, say, no more than half an hour, I'm perfectly fine if I converge to, I mean, after several hours. I mean, I don't want it to take several days, but I don't need to have a closed loop dynamics that kind of is at the same speed of the plant. I mean, I can allow myself to a much slower dynamic. That's fine. I mean, the more challenging aspect is kind of to deal with the noise level, the imperfect understanding of plant gain and plant seasonality. Mm-hmm. I mean, but we are kind of getting into a completely different ball game when we're starting to talk about those other problems here, because when we're having constraints related to conversions, where we may have that if I show an ad today, I mean, it may take several days before someone converts. Because I think depending on what type of ads, if I'm showing an ad where a conversion is defined by the user clicking on the ad, I mean, then we're talking about in the terms of seconds, because either they click or they don't click. They're not going to think about that for longer. But if I show, for example, an ad for a car, well, first of all, it's a very small chance that people will buy a car online. But if they do, they will probably go home and they will talk to their spouse and check their finances. Can they afford it? And a few days later, they decide to buy it. So then we're having that sort of long latency. And I mean, other examples that might be if we're running a campaign for, say, TurboTax, we may show ads kind of in January, but people don't start to consider filing their taxes until in March. And then we have this very the latency is not only you can describe it by time varying dynamic, because I mean, the closer you get to April 14th, I mean, the shorter the latency might be, because you know that kind of that is your deadline to file your taxes. So those, I mean, when we're adding kind of those types of dynamics effectively, but kind of that we are thinking about it, okay, the distribution of that lag that can be described by different type of sort of statistical distributions, but then that can be translated into sort of dynamics that, from the controller's point of view, that would be a dynamic that could be of first or second or third order or whatever, or could be time varying as well.
Thank you very much. So our students are probably asking themselves, how do I get into a career like this? Not this specific career, but how do I end up with such an original career outcome like this one in something that right now nobody even knows exists, but 20 years from now it's something incredibly impactful and relevant. So that's what they may be asking. I bet they, many are. Are there any questions you guys want to ask Nicholas? Okay.
I mean, so while I mean, if there's a student have questions, I mean, while you are thinking about what to ask, I mean, I just encourage you to be open-minded and I mean, don't underestimate, I mean, what you bring to the table, because with a background in controls and dynamical systems, I mean, you may face a technical problem, engineering problem, but allow yourself to kind of think outside of the box. Try to do this abstraction, because that's really what we are trained to do. I mean, you see a problem, it may be in a completely different domain. I mean, how can you bring that problem up to describe that as a block diagram and in differential equations? I mean, that's kind of, if you can sort of just achieve that, I mean, then you have this huge toolbox with everything you have learned kind of in your studies at UCSD. I mean, then there's so much you can do. So, I mean, just remember, I mean, someone may present you with a problem, but don't just kind of assume that the way they present the problem to you is the way to look at the problem. Kind of try to really bring it up, do this abstraction, bring it up one level and see how you can actually leverage on things that you know from other problems.
Okay, thank you very much. So thank you for speaking to us today. Let's keep in touch. Let's keep us in mind if there are internships at Yahoo in that area for students or any other types of closer partnership in research and in training. Okay, have a great weekend.
Thank you very much, Dr. Carlson. It was a pleasure to host you. Thank you, Professor Krstić, and thank you all for attending. Have a great weekend.
Thank you very much for having me.